Hello everyone, welcome back. Hope you guys are doing very well. Uh, in this lecture, we're going to be discussing about CMOS power. There have been some requests about power analysis. What do we do? How do we do during VLSI circuit design at a very high level, let's say SoC integration level. But before going into detailed power analysis, we need to understand what is power and energy, or what is in other words CMOS power. So let's have a quick discussion about it. This is a typical VLSI flow we have discussed multiple times. Very simple. You have a RTL, then you convert that RTL to logic gates. During logic synthesis process, you got the gate netlist, and that gate netlist goes to further back-end design tools. I call it place and route activity. There are many other steps in between, however we are not discussing here. We can think of that we're going to be doing simulations, equivalency checking, running other tools, linting tools, all other sorts of activities, physical verification, and all. Okay. Focus of this lecture is power analysis. Definitely we have, after writing RTL, we have questions in our mind. Whatever RTL we have, or whatever the logic circuit, or whatever the chip design we have, is it a good RTL which can produce low power or power optimized gate netlist, or can we do some changes? Okay, that's a very simple question comes when we start designing our logic circuits. Then naturally, after we convert RTL description to gate netlist, we're gonna be asking by ourselves that what is the power profile of a synthesized gate netlist? Because if we are not aware of how much power this particular netlist is gonna be consuming, we can end up in problems during backend activity, because backend tool also would add certain kind of extra structures. Also, during the backend activity, you have the library information or of a particular technology. Okay, so we need to be aware of how much power our chip is going to be consuming, and in the end, we want to know that whether our final chip layout is optimized for power or not. Think about for a second that if your cell phone, okay, think about the chip inside the cell phone. Okay, if it's getting heated up too much, it will lead to higher temperatures, and would you be able to hold that phone after few hours of continuous operation in your hand? Think about it. So we definitely need some solution which can answer these questions to us. Naturally, it boils down to we need to do some kind of analysis. Good. So we do power analysis at different levels during our design process. We do power analysis at RTL level, RTL power, which is a very rough estimate because we don't have actual physical information of the design. Okay, however, it's a good indication at the RTL level itself that okay, if it's gonna be out of budget, then we can still do something at the RTL. Then we can run power analysis at the gate netlist level and at the chip layout database after the place and route. We definitely need that analysis, whether our chip is gonna be consuming power which is within the spec. All right. Let's talk about energy and power. Very simple basic concepts. Energy and power. Energy. How much work do I need to do to move a charge through a voltage difference? All right. So imagine a charged particle is moving from voltage V1 to V2, okay, or potential V1 to V2, let me say that way. A charged particle is moving through a voltage difference and we call it a voltage, let's say V. How much power? Okay, what's the power? Power in simple sense is energy per unit time. Good. So how much energy would I consume to move a charged particle, let's say charge Q, through a voltage difference V, or in other words, charge is moving from a potential V1 to potential V2, so V would be V1 difference V2 or V1 minus V2. Good. So that would be the total energy I would need. So how much power is going to consume? Simply energy divided by time, energy per unit time. Good. Let's call it equation 2. All right. We have two kinds of circuits, AC circuit and a DC circuit. First, let's talk about AC circuit. Okay. We have a voltage, resistor and capacitor. Typical RC, simple RC circuit, AC circuit. So how much energy or power, let's talk about energy, how much energy would be needed to charge this capacitor. Okay. So charge Q is moving through the voltage V, so energy would be Q times V. And how much charge Q, whatever is the energy stored in the capacitor. Good. So Q we can further simplify, C multiplied by V, and then V is as it is. So we end up getting a energy equation, C capacitance times voltage square. Let's call it equation 3. Good. What would be the power? Power would be simply E divided by T, or in other words CV square divided by T. Let's call it equation 4. We can further simplify it. T is nothing but let's call it a frequency, okay, that at which rate or time interval 1 over T is F. Let me call it here F. Don't confuse F with your clock frequency. Good. Question number 5. So this is our dynamic power. Okay. So F here, F is nothing but the inverse of the time. Okay. For whatever time interval we are talking about, let's say capacitor is taking T time unit to get charged up. Good. So that would be 1 unit, but let's say we can call it over the multiple such units. So that is represented by T. We already know that P equal to CV square F. F is nothing but the inverse of the T. Now, interesting concept here. If a node toggles n times over the time interval T, okay. So here node can be anything, any signal for example, or for example, you have a netlist, you have different points at the netlist, you may think of those as nodes. Good. This node came from the simple fact that at the end the algorithms would be processing this whole netlist in terms of nodes and the edges. So nodes will become the vertices in a graph, and edges will become simply the connections between nodes, and a net or a wire can be split into different pieces connected via nodes. Good. So if a node toggles n times over a time interval t, we can conceptualize, think in terms of it is toggling from 0 to 1 and 1 to 0. Okay, it's a simple data signal. You can think of a data signal, okay, toggling n times over a time interval t. So this f factor, the f variable, would become n divided by 2 times 1 over t. Why we are taking half? Because we are interested in knowing how much energy is consumed to charge up the capacitor, because that was the energy would be needed to move the charge from here to capacitor, okay, or from the voltage source to the capacitor. So half of the n. All right. Let's call it equation number 6. And if there are k clock cycles within the time interval t, then t would simply, the total time would simply will become k times t clock. Now we are talking about the clock frequency here, okay. So t clock is nothing but 1 over clock frequency, or the time period of your clock, actual clock. Good. Good. We have just substituted the value of the time period of the clock. Good. Let's call it equation number 7. So clock frequency is inverse of the clock period. Simple that way. Now if we substitute all these values back to the equation for the f, which we just discussed a few minutes back, we end up getting a new equation of the f. Okay, f equal to n divided by 2 times frequency, clock frequency, divided by k. Okay, or we can rearrange it and put it in a different form, that n divided by k times f clock divided by 2. Now in this equation, n is a variable, k is a variable. Good. So we can collectively term this n divided by k as alpha, and that alpha would become our activity factor. Okay, and this is the equation for f, activity factor times clock frequency divided by 2. All right. We can substitute the value of n, okay, divided by k, and the f in our original equation, and we end up getting an equation for dynamic power. C, capacitance, voltage square multiplied by activity factor times clock frequency divided by 2. This is a dynamic power equation. All right. So can we calculate the dynamic power? Yes. Now the switching factor depends or the activity factor. Okay. So let's say if your data signal, okay, data signal is toggling 10 times And how do we know that? Well, we have to run certain test vectors and see how many times on an average the data signal is toggling, and that would become our activity factor, and that we should be using along with the clock frequency, capacitance, and voltage. Okay, capacitance we can get from the extraction tools after the layout is done. So that's a tricky part. We need the parasitics information, okay, or we need the load capacitance and capacitance information, capacitance of different wires and nets, or in other words, SPEF format, standard SPEF, standard parasitic extraction format. Different EDA tools can extract that information, which is needed for other tools as well. Let's say timing analysis, prime time, to reflect the true or close to true value. In this whole equation, there is no resistance term. Interesting. Good. So we are only dealing with the capacitance and the voltage, activity factor, the clock frequency. That will give us the dynamic power. Now let's talk about the DC circuit. So far we were talking about AC. Now let's talk about DC circuit. Okay, this is a DC voltage source. Okay, and the resistance. Good. Energy Q times V, or in other words, for a DC circuit, you can substitute the value of I is the current and times T, time interval times V. Okay, and the power simply E divided by T, or IV, current times voltage. That is for the DC circuit. And this is a static power. Good. There is this amount of power will be dissipating no matter whether capacitor is charging or discharging. It's a static power. Good. A total power would be static power plus dynamic power. Now here we cannot control that much of the static power. That depends on the on many factors, but it's a more or less a leakage power. Okay, and again goes back to the dependent on the technology, leakage power. We can somehow think about controlling the dynamic power. Okay, increasing the clock frequency, decreasing clock frequency, and whatnot. Okay, and capacitance. Okay, we can see how much the capacitance, extracted capacitance of this net, and how we can reduce it. So we can do something about the dynamic power, but we cannot do anything much about the static power. Good. And remember the equation of the dynamic power. Okay, the frequency term F comes, and it is a square of the voltage. Okay, proportional to the square of the voltage. So voltage will have very big impact on the dynamic power. So that's why we talk about, you might have heard the term, okay, you know, our chip is working 1.5 volt, now it's 1 volt, now we are talking about 0.7 volt. Okay, we are continuously decreasing the voltage because of the power component. And the major reason is the power consumption, power component, and that in other words leads to the higher temperature. If power is high, is directly proportional to temperature, but temperature is not as simple as the current. That's a self-heating phenomenon as well comes in picture. That's a separate topic we will discuss some other time. The equation for the total power is simply IV plus CV square alpha clock frequency divided by 2. Good. So as you can see here, proportional to the voltage square. Now, how these things apply to our CMOS? Good, very interesting thing. So far we discussed basic equation. In detail you can find all these mathematical equations from a textbook. But the important idea here is to understand the concepts. So this is a typical inverter circuit. We have PMOS, we have NMOS. Good. Let's first talk about the static power. Okay. So you apply 0 or 1 at the input and you get 1 or 0. Okay, and this circuit is in a steady state. A certain amount of current flows from the ground, from the VDD to VSS, and we call it a static leakage current. Okay. That leads to a static power or leakage power. Okay. Now another interesting thing, because after applying the voltages to V input, you don't directly immediately jump to the steady state. Okay, let's say you can look into different phases of operation of a inverter. We call it IV characteristic curve or IV characteristic graph or basic PMOS and NMOS operation. You can look into the textbook. So before reaching to the saturation region, okay, the device operates in different regions, and in different regions different kinds of current flows. But when the device is in operation, it's a static leakage current which flows from VDD to VSS, leads to a static leakage. Now let's try to complete the circuit and put a load capacitance here, and let's think about a case where the circuit is not yet in saturation or operation mode. Okay, where the voltage applied is bigger than the threshold voltage for the NMOS and less than the VDD minus threshold voltage of the PMOS. Interesting scenario. Good. So what happens in that region of operation? There is a short circuit, a small short circuit current flows from the VDD to VSS. That leads to short circuit power. All right, that's again a component of static. Well, it shouldn't be static, but kind of static. But this is not always. This is only when the circuit is not in, haven't reached in operation mode yet. So this is for only for short time. Short circuit current flows from VDD to VSS. So I instead of putting in dynamic, we can call it part of a dynamic, but let's call it simply short circuit current under the condition when input voltage is bigger than the threshold voltage of the NMOS and less than the VDD minus threshold voltage of the PMOS. All right. Now this short circuit current has interesting characteristics. It increases with the size of a transistor. Very interesting. So if you have a bigger area, bigger transistor, which we may need for for many different reasons in the chip, we may use them. So that the short circuit current increases with the size. It decreases with the load capacitance, another interesting feature of this current, and it is maximum when capacitance is 0. All right. So these are practical observations from the lab. But instead of getting into detail, we just need to have some idea or some awareness of what are the different power components. Now let's talk about when we apply voltage. We apply 0 at V in, okay, and we assume after some time the inverter will start working. So when V in is 0, PMOS is on and NMOS will be off. Good. And a current will flow from VDD to V out, or the charge, let me put it charge, and that will charge the capacitor up, okay, and after some time that capacitor would be charged, or load capacitance would be charged, and we will get the 1 value at the output. So input is 0 and output is 1. Okay, these are logical levels. However, in reality they would have a certain voltage level enough, maybe 0.6, maybe 0.7, but after, so that we can classify that voltage level as 1 or maybe 0.01, we still can call it logic level 0. Okay, capacitor is charged and we have a power component which is responsible for charging the capacitor. That much power we need. Good. Now other way around, when we have 1, logic level 1 at the input, then PMOS is off and NMOS would be working. Good. And now C, or capacitance, is, this capacitor is charged up already. Since this NMOS is on, it will offer a path for this charge to go to the ground, or VSS, and the capacitor will discharge after some time, and we will get logic level 0 at the output. Clear? The capacitor is charged. How much power? Discharged power. Dynamic power, we can say components of dynamic power: short circuit, charged, how much power we need to charge the capacitor, and P discharged. Okay, those are components of dynamic power. All right, and dynamic power is only when there is a switching activity. If your signal is static, it's not switching, so there is no component of the switching, there is no component of dynamic power, only the static power is there. That's why it's very important to have right set of test vectors to get a good picture of dynamic power. If your test vectors are not exercising the signals properly, then you may not get a good number for the total power, because the signals which are not switching due to your test vector, those will be static and the dynamic power component would be 0 for them. It's important to have a good test case or test vectors which can exercise most of the data signal, control signals, or static signals in your chip, or in your block, whatever you are running power analysis on. Good. Just a recap: total power, static plus dynamic. Who can help with the power analysis? Well, industry standard tool Power Artist can help us to analyze power on our chip, and this tool is very sophisticated, very good tool. However, the analysis results are only good if you provide good inputs to the tool. At the RTL level, you can provide the RTL files, .vvhtl, it would need the library information. Also, it would need a pace model. If you do not have a pace model, one needs to create a pace model first before running the power analysis tool. What it is nothing but the tool first characterizes, okay, your existing design. Let's say you are working on a microprocessor V.2 and you already have an existing design V 1.0. So you can give the physical layout or information to the tool and generate a pace model, which would be needed by the tool in order to give more accurate results at the RTL level. Otherwise, the results would be very rough and would not be reliable at RTL. Okay. VCD format or FSTB format for the test vectors, or you can run a test case and you can choose a certain window where there are different signals are switching. So why this is needed? Well, tool internally calculates the activity factor for the different signals, and basic setup of which is needed by the tool. Important here is the RTL file and your good stimulus in the form of VCD or FSTB, and a pace model file. Library files for let's say if you even do not have pace model, then tool may use wire load model or different other parameters from the library. Live is anyway needed when tool is gonna be working with the standard cells or other library elements to get the information. Now here we are talking about not the synopsis lib, here we are talking about the power lib. Okay, so synopsis libs also would be needed by the tool for certain other information, but there should be Apache Power Artist characterized libraries, okay, power libraries in your library directory. Okay, when you have the gate netlist, you can give the gate netlist to the tool, and when you have post routed netlist, that you can give along with the SPEF file. Now, and after this post layout netlist, tool will give more accurate results. However, it is important to check at the RTL level. What if you're just too far off that even at the after synthesis you can't do anything? I mean, only very limited thing can be done after the logic is being synthesized, but more power savings or low power techniques you can use at the RTL level to code RTL in a certain way so that the synthesis tool gives you a more optimized logic. That is one way, and at architectural level you can save more you can save more power, in other words. Good. So for this lecture, that much. In another lecture we can talk about some tool specific things. However, most of these EDA tools are proprietary, and it's very difficult to get the information from the EDA tool vendors. Conceptually, it's very simple setup. Anybody can run. You just need to know basic things, which I have covered here, that lib models, okay, or library pace models. If you don't have already, then you may need to generate using an existing previous design for that particular technology node, let's say 700 or 14 nanometer, and that you can use to get estimated RTL level. And VCDs, FSTVs, those are basic things which you can get it from the verification engineer. They can write a good test case which can exercise most of the signals in the particular logic module. So basic things. So after you give the basic after you have done with the basic setup of the tool, then run the tool, and the tool will give you analysis, and tool will also guide you further where in RTL you can optimize more in terms of low power. Tool can guide you, okay, I'm getting 60% of the clock gating, which you may consider to increase up to 90% or 95%, means that at certain portion of the design you may use clock gating, which tool is suggesting you that you may use further clock gating. Okay, just for one technique. So tool is very good to run at RTL level. I'm not advertising here for Power Artist. There are other vendors like Synopsys, Mentor Graphics, Cadence. They all have power analysis tool in their ASIC design tool portfolio. Basic concepts are same no matter what tool do you use. All right. And then when you have synthesized netlist, you may want to check whether the netlist is optimized for power or not. If it's not optimized, then you may go back and fine-tune the logic synthesis tool. You may further constrain it in different ways, which are vendor specific, to give you a good netlist. And after that, then netlist goes to the backend tools, and after place and route, all the physical geometry information is available, means that we have more accurate capacitance value, which tool can use instead of pace model to give you more accurate, better power numbers. Okay. All right. Thank you very much, guys. If you have questions, feel free to send me an email or message me, or if you are looking for some other specific topics, you can also contact me for any other help. Remember that if you really want to have my consultation or lectures by me, we can set up a time. However, I typically avoid it unless it's a big group of people. Then we can arrange a sort of workshop for different areas of ASIC design. Let me know how does it sound to you, and you may also suggest me some other topics of your interest, which you find that your professors are not teaching you very well and you need some extra help. I'm very much happy to help you. Usually many of the technical things are not covered at many universities. Unfortunately, it's the way it is. They're like the practical engineering is practical, and unfortunately at many universities they ask you to write big exams, theory, blah 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 blah, but you got to focus on the practical things more if you really want to do good in engineering. Don't take me wrong that theory is not needed. Theory is needed, but theory is theory. Let's say who is going to talk about that more than the physics you learned at university, it is more scripting which you may need at the industry. Okay, so you got to have a good knowledge of different things. All right, thank you very much, and I hope you all the best. Please subscribe if you like. That way I comes to know that okay, people are liking it, and don't forget to don't hesitate or don't forget to comment or send me a message if you really need help. But I receive lot of emails, lot of messages, comments. Sometimes it's very hard to respond them everybody back, and sometimes some arrogant people also come. So you know, just be nice, and if you are really needing my help, I can help you. All right, thank you very much. Have a wonderful day. Bye for now.